Okay, so we have changed the link actually. So I have removed latency. So now you can see it clearly. Yeah. So we are resuming it. So just for a quick, sorry for the glitch. So you can just give me if you're there, your attendance if you're there, so that I can start. I can be sure of that you're there. Yeah. So who all are watching? Okay, sorry guys. So there was this glitch. Now it should be fine. So let's start our. Well, let's resume. So we were dealing with the Thales theorem, right? So we dealt with Thales theorem. I told you that basic proportionality theorem or Thales theorem is nothing but this: that if there are two triangles, if there is a triangle ABC and a line which is drawn parallel to DE, a line DE is drawn parallel to BC, then AD upon DB is equal to AE upon EC. That's Thales theorem. And the next one is the converse of this. This is also called basic proportionality theorem. So let's quickly revise that as well. Okay, so the next one is, if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side of the triangle. So again, if you see, this is our triangle. Let's say we draw a triangle. So if we have a triangle like that, and we are saying that there's a if there's a line which divides this triangle ABC, the sides of this triangle, in such a way that AD upon DB is equal to AE upon EC, then we say that we declare that DE is parallel to BC. DE is parallel to BC. This is converse of BPT. Okay, so keep that in mind. Now, how did we prove that? We used something called contradiction. I'm not going again into deeper details. Contradiction will be used. Contradiction means, let us say that given this ratio is there, let us say that DE is not parallel to BC, and we say that let another point DE dash be there on AC such that DE dash is parallel to BC. Then by our BPT, we can say that AD upon DB is equal to AE dash upon E dash C. Why? Because this is just what we proved, that if DE dash is parallel to BC, then AD upon DB will be equal to AE dash upon E dash C. But if you see, the given is this was given. So that means from this relation and this relation, we can say that AE dash by E dash C is equal to AE upon EC, isn't it? Now, if that's the case, that means there are 2 points on AC which divide AC in the same ratio. That's not possible, and hence we say that E dash must be equal to E. That means E dash must coincide with E, and hence we say that DE will be parallel to BC. That's how we proved converse of BPT. Okay, fair enough. Now, so let's go to the next one. The next slide says the internal bisector. This is called internal bisector theorem. So these are the basic theorems we must remember. The internal bisector of an angle of a triangle. So let's say if there is a triangle like that, ABC is this, ABC is a triangle, and there's internal bisector of an angle. Let's say angle A is being bisected such that this is D. So A angle, if this is angle theta, this is angle theta, let's say. The internal bisector of an angle of a triangle divides the opposite side internally in the ratio of the ratio of the sides containing the angle. That means if AD is internal bisector of angle BAC. If that is true, then we know it is BD upon DC is equal to AB upon AC. So these are the sides containing the angle AB and AC. So angle A is being bisected. So hence AB upon AC will be equal to BD upon DC. So hence you remember like that, AB upon AC is equal to DC. Yeah, this is angle bisector theorem. Again, so how would you prove it? So if you remember, to prove this, you have to extend AB, in this direction such that AC is equal to, let's say this point is E. And then again using BPT, if you really remember, in this case, what we basically did was we extended BA to AE such that A is equal to AC. Now, if A is equal to AC and these two angles are same, and then if you or what you can do is you can just yeah. So if this side is equal to this side and this angle is equal to this angle, right? And if you see, so it's given that AB by AC, or yeah. So basically, we have to prove that AB by AE is equal to BD by DC. Then our job is done. That means somehow you have to prove that AD is parallel to CE if this angle is equal, or these two sides are equal. Or alternatively, what you can do is you can produce CE in you can make CE parallel to AD and let BA extended join CE at this point. Okay, so using these, so this is how and then using BPT you can prove that AB is equal to, or AB by AC is equal to BD by DC. So again, since this is a revision class, I will not go into the basics of it. You can always revise through the text which we have already discussed in the class. So I'll just skip these proofs. So let's go to the next proof, okay, or next theorem. So next theorem is, if a line through one vertex of a triangle divides the opposite side in the ratio of the two sides, then the line bisects the angle at the vertex. So basically it's converse of the previous theorem. So if you see, this is nothing but converse of the previous theorem. Converse of previous theorem. What was that? And what does it say? So basically, if again you have a line joining, let's say, A, B, C, and then you have, let's say, this is BD. Okay, so if D is the point on BC such that it's given that BD by DC is equal to AB by AC, then angle BAD will be equal to angle DAC. This is what the theorem suggests. So I would do one thing, because we have lots of slides to cover. So what I'll do is I'll just try and recap the theorems first, and then as time permits, we'll come back and see how many proofs we can deal with. Okay. Now, this is, so keep these theorems in one place, as in we have already recommended that while solving problems. Keep these theorems in mind. Next is the line drawn from the midpoint of one side of a triangle is parallel to another side and it bisects the third side. It is a direct fallout of Thales theorem. So let's again understand what exactly is this. So there is a triangle. There's a triangle, and this is A, B, C. And we say that line drawn parallel from the midpoint of one side. So let's say this is E is the midpoint. E is the midpoint of one side of a triangle and is parallel to another side. Let's say we draw a line EF, or let it be D instead of this being E, let it be D. Okay, so let us say this is point D, and it's given that D is midpoint. D is midpoint of AB. Okay, D is midpoint of AB. So what does it mean? AD is equal to DB. And then we are drawing a line parallel to BC. So clearly, you can understand from this direct result of Thales theorem. If DE is parallel to BC, then we know that AD by DB will be equal to AE by EC, right? By Thales theorem, and hence the first part of this thing is proved. So hence AD by DB anyways is 1. So hence AE by EC is equal to 1, and hence E is the midpoint as well. E is the midpoint. Okay, the next part of this is, let me just clear the surface a little bit. Yeah, next part of it is, or just a minute, I'll just take it. Okay, so, and the next part, I'll just remove this part, cut and delete. Yeah, so the next part says that DE is, now once E is midpoint, so you say, yeah, the other part is DE is half of BC, right? And if you remember, I'll give you the hint how it was done. So you had expanded DE to EF, and such that DE is equal to EF. Then what will happen? You will say that if DE is equal to EF, A is equal to EC anyways, and this angle is equal to this angle. So triangle ADE is congruent to triangle CFE, isn't it? Once that is done, that means this angle is equal to this angle, and hence this angle is equal to this angle. So basically, by this you will, so basically DBC is equal to DFC. These two angles are same. And what else? If you see, so basically DFCB can be proven to be a parallelogram. So this is a parallelogram. How? Because this angle is equal to this angle. That means CF is parallel to AD, which is parallel to AB. So CF is parallel to AB, and AD is equal to DB is equal to CF. Why? Because by congruence we proved AD is equal to CF or FC, and AD was anyways equal to DB. That means DB is equal to CF, and we just proved that AB is parallel to CF. That means DFCB is a parallelogram. That means DF is equal to BC, and DF was nothing but 2DE is equal to BC. So DE will be equal to half BC. right? So this is the next theorem. Next, let's go to midpoint theorem. This is also called midpoint theorem. Okay. Now, yeah. Oh, sorry, we missed this card. The external bisector of an angle of a triangle divides the opposite sides externally in the ratio of the sides containing the angle. So what does it mean? This means simply this. Similar to internal bisector theorem, we have external bisector theorem. So let's say ABC is a triangle and BA is extended. Okay, and let's say this is my, so don't go on the scale. It's not to scale actually. Yeah, no worries. So let's say this theta is equal to this theta, and let's say this is A, this is D. Okay, so D is the AD. AD is external bisector, of angle CA, and let's say this point is CAE. Okay, so if that is so, then we know that AB upon AC is equal to BD upon DC. Okay, that's what it will be, right? So how to remember this? So you start with AB and AC, and hence you also start with from this point B. So let's say AB is the first side, AB, and then B is the starting point of the side on which the point D lies. Then you first stretch out from B to D and from D to C, like that, right? So hence AB upon AC will be equal to BD upon DC, like that. Okay, so this is external bisector theorem. Okay, let's move on. So this is done. Cards 8, 7 is done. Yeah, so internal angle bisector theorem, external bisector theorem, midpoint theorem. Now, the line joining the two midpoints of the sides of a triangle is parallel to the third side. Again, a result of converse of Thales theorem. So you can prove this by converse of Thales theorem. ABC is a side, and let your D is the midpoint of AB, and E is the midpoint of AC. Then DE is parallel to BC. DE is parallel to BC. Converse of this can be proved by converse of Thales theorem. How? So AD by DB. So clearly AD by DB is equal to AE by EC is equal to 1 by 1. So hence, since the ratios are same, by converse of Thales theorem, DE will be parallel to BC. Okay. Next, so let's go on to our diagonals of a trapezium divide each other proportionally. Okay. So let us understand this. What is this? Diagonals of a trapezium. So what is a trapezium? Trapezium is a quadrilateral having two sides parallel, and the other two sides need not be equal. Okay, if they're equal, we call them isosceles trapezium. ABCD is a trapezium. ABCD is a trapezium, and the diagonals of a trapezium. So let's say diagonal AB and diagonal AC. Okay, so let's say this point is O. So what does this theorem say? The diagonals of a trapezium, that means OD upon OB is equal to OC upon OA. Okay, so they are dividing each other proportionally. And again, very easy to remember the proof. What you do is you just draw a line parallel from O onto and join it with AD, and let this point be E. Okay, so and then you can also so from here you will get, what will you get? You will get in triangle DAB, what will happen by Thales, again by BPT, since EO is parallel to AB, then DE upon EA is equal to DO upon OB. Mind you guys, I'm not writing all the statements because again, this is a revision session, so we'll try to give you as many hints and you have already gone through it. I'm just trying to recap everything. So hence, you should not be writing like these when there is a question on proof. You should not adopt this methodology. For all the questions, previous year's questions, we are doing a detailed model answers writing technique. So hence, you can always visit those videos to see how the answers should be written. This is just to recap whatever we have learned, so that you can retain these during your exams and you can apply them. So D upon EA is equal to DO upon OB by Thales theorem. And by Thales theorem again, you in triangle, this was in triangle DAB. Similarly, you can also take triangle, and then now you can take a triangle ADC. ADC. In this also again, AE upon ED is equal to AO upon OC. AO upon OC. So if you see these two, using these two, you will see, and you have to see, for example, here AE upon ED is there. Here it is the reciprocal of that ratio. And hence, if you reciprocate it, it will become OB by DO. And if you equate them, you'll get AO, this particular relationship. Yeah. So it falls out directly from here, right? So that's how you can prove this theorem. I hope you guys are connecting to it. If you want me to revisit any particular this thing, you just let me know. Okay, you can note down the card number. If the time permits, towards the end, we'll always come back. Otherwise, we can always take them offline and discuss it. Okay, so let's go to the next slide. Next slide says, if the diagonals of a quadrilateral divide each other proportionally, then it is a trapezium. Again, converse. So let me, yeah, so this is the converse of the previous theorem itself. So converse, again, this is the converse of the previous slide. So what does it say? It says that, let's say there is a trapezium. Okay, let's say this is a trapezium, A, B, C, D. And if they are, let's say if there's a diagonal, there is a diagonal which is like that. And yeah, and this is O, and it is given that AO by OC, AO by OC is equal to, let's say, BO by OD. Then sorry, this is a quadrilateral. It's not a trapezium. I'm sorry. So if there is a quadrilateral and the diagonals are not bisecting, dividing each other proportionally. So this is how they will divide proportionally. Then we have to prove that. Then we have to prove that ABCD is a trapezium. ABCD is a trapezium. So how to do that? Okay, so let us say that we draw a line parallel to so again, you can take this as you find a point E such that if you find a point E on AD, you can always find a point E on AD such that AE by ED is equal to AO by OC. Okay, there's no problem. So you can find a point E on AD such that AE upon ED is equal to AO upon OC, and hence which is equal to BO upon OD, because this was given anyways. Yeah, so that means you have to take first this combination. Which combination? So these two. You have to take these two, and then if you take these two ratio, then by converse of BPT, you can say in triangle ADC, in triangle. So from this, what follows in triangle ADC? In triangle ADC, what happens? EO becomes parallel to DC, isn't it? By converse of Thales theorem. And then if you take these two together, that is these two together, not these, basically AE by ED is equal to BO upon OD. If you take these two ratios together, then what will happen? You will see that OE is parallel to AB. OE is parallel to AB, and then you can combine these two to get what? You can get AB parallel to DC. That's what, if you prove this, that means ABCD is a quadrilateral with two opposite parallel sides. That means it is a trapezium. Okay. Next. So let us now go to next slide. And this is okay. So yeah, any line parallel to the parallel sides of a trapezium divides the non-parallel sides proportionally. Now, instead of diagonals, now they're talking about, let's say if there is a trapezium and any line parallel to the parallel sides. So let's say if I draw a parallel line like that, then they're saying if this is A, this is B, this is C and D, then they're saying, let's say this is D and, sorry, this is not D, this is, wait a minute. Yeah, this is E and this is F, and it's given that EF is parallel to AD is parallel to BC. EF is parallel to AD one side and it's parallel to BC. Then they're saying that AE by EB is equal to DF by FC. Now, how to do that? So you can do it multiple ways, and one is you produce the two non-parallel sides to meet at, let's say, O. Okay, from here, if you see, you get what? Again, I said that I will not be covering proofs, but then quickly, if it is possible, let me just try and cover as many as possible. So OA, so in triangle OEF, again OEF, what can I write by BPT? In this triangle OEF, AD is a parallel line, so I can say OA by EA is equal to OD by DF, isn't it? Similarly, in triangle OBC, we can say OA by OB is equal to, or rather OA by AB. Just a minute. Just a minute. I'll delete. Yeah, OA by AB. OA by AB is equal to OD by DC. Okay. Now what you do is you divide 1 by 2. 1 by 2. If you divide 1 by 2, you will get AB by EA. AB by EA is equal to CD or DC, whichever way. DC by DF. DC by DF, isn't it? Now I am writing in this side and then subtract 1 from both sides. You will get AB by EA minus 1 is equal to CD by DF minus 1. And if you solve it, you'll get AB minus EA on the left hand side, which is nothing but, so I'm just writing it here. So it's nothing but AB minus EA. So if you take the LCM and all, you'll solve it, you'll get AB minus EA upon EA. Now AB minus EA is BE. So you'll get on the left hand side BE upon EA. BE upon EA. And on the right side, CD minus DF is CF. So you'll get on the right side CF upon DF. So if you see, friends, this is nothing but this, or the reciprocal of that, right? So hence you proved this as well. Okay, so yes, Ruhi is asking some question. I didn't get, Ruhi, can you please type it there so that I can, solve it in the second run. Okay, let's move ahead. Okay. If 3 or more parallel lines are intersected by two transversals, then the intercepts made by them on the transversals are proportional. Okay, I might be, mistyping or miswriting and, doing some thing, but, you can highlight that and then, we will do a correction. So if 3 or more, wait a minute, again, if 3 or more parallel lines are intersected by two transversals, that means if, let's say there are 2 or more parallel lines. So they're saying there are, oh, sorry, just a minute. Yeah, so they're saying, let me just delete this. Okay, so there are 3 or more parallel lines. So let me draw some parallel lines. And I will take this color. Yeah, okay. So parallel line 1, then another one, parallel line 2, and then parallel line 3, like that. Okay, and then it is intersected by two transversals. Okay, so this is, let's say this is one and this is another. Okay, then the intercepts made by them on the transversal are proportional. Okay, very good. So what does it mean? So let's say this is A, B, C, D, E, F. Okay, okay, A, B, C, D, E, F. Then they are saying AC upon CE is equal to BD upon DF. Yeah. So this side upon this side, or intercept, is equal to this side upon this side, which is again very easy to prove. How you produce this? You produce this, and then again take triangle ACD first, and then take triangle AEF with AB as the parallel line, AB parallel to CD. So you first take this triangle, which one? ACD. From that you will get, let's say this point is O. So from that you will get OA upon AC is equal to OB upon BD. And then take triangle OC or OEF. In that you will get OA upon AE is equal to OB upon BF. And from whatever we just proved in the previous card, you can use the same to prove this. I hope this should not be a big challenge for you guys. Okay, same again. So far we have been doing applications of BPT. Okay, and just to add here, I will also tell you that in BPT there are multiple corollaries. So hence you must be knowing, and you can always quote this in your exams while proving sums. So let's say ABC is the triangle, and this is DE is parallel to, so DE is parallel to BC. Then all are true. What all? AD upon DB is equal to AE upon EC. Also, AD upon AB is equal to AE upon AC. Also, DB upon AB is equal to EC upon AC. All these three are true. You can do it by adding +1, -1, and things like that. So there's a question that in card 13, okay, let me go to card 13. So card 13 says, wait a minute. So in card 13, yeah. So in card 13, can we just construction a diagonal and prove it? Yes, you can do that as well. There is no problem, Kritika. So you can do that as well. Whichever way you want to, both are there. There could be multiple ways of proving the same question. What question Kritika is asking is this. Let me share it with all other people. So there are three. Let me just now delete this. And in this card, she's saying if there are three lines, this is not parallel, obviously it doesn't look like. So this is, let's say there are three lines parallel, and there are two transversals like that. So what she's saying is, can I join these two and prove? You can definitely prove. How? What is the proof? So let's say all of you would be knowing it. A, B, C, D, and E, F. So again, by application of BPT, let's say this point is O. So AC upon CE is equal to BO upon OE. And again in triangle BEF, it will be BO upon OE is equal to BD upon TF. This is also valid proof. I hope I cleared this. Next, let's go on to our slides back. Yeah. So you could also do this when taking ABF and trapezium using the rhyme property. Yes, Param, correct. You're correct. So you can use. Thanks for adding to that. Okay, so card 13 is done. Card 14 is done. Sorry. Okay. Yes, I was answering Param's question. So Kritika, your this thing also be done in the same way, which I just proved for card 14. So the drawing which I did here was for part 14. So that's a correction. Next is, okay, now comes the second part. What did we discuss? We discussed these three parts, isn't it? So triangles, basic proportionality theorem. So far we learned around 14 theorems, or let's say 14 piece of information around basic proportionality theorem. It included midpoint theorem, it included internal and external bisectors theorem. So all should be there on your fingertips. Now we are entering the second realm, and that's similarity of triangles. Let's see how. So first is the criteria for similarity. So we learned criteria for similarity in some slide back, and we said that corresponding angles must be equal and corresponding sides must be proportional, isn't it? So yeah, so we, for two criteria for similarity, which has to be true. It's another thing that we need not check everything for its validity, but here, so we have some ways to reduce our checking criteria, but then this will definitely be true always. What all? Corresponding angles must be equal. This is point number 1. And 2 is corresponding sides must be proportional. Sides must be proportional, isn't it? Proportional. So these are the two criteria. Now you don't need to check each and every criteria for checking the valid, or let's say similarity of two triangles. So hence we have some, you can eliminate your requirements. So not all there. So hence there is 6 criteria, right? There are 3 angles and 3 proportional sides. Okay, so let me say. So actually, if you see, that even if all the 3 angles are same, let's say this angle A is equal to D, and B is equal to E, and C is equal to F, then also the two triangles are similar. And I will just try and do one proof for you. The rest you can always you can use a similar method to prove all these criteria. Though usually they do not ask proving problems or criteria proving problems in boards, but you must know. Okay, so hence if you see, what do? I will select a point E dash on AB such that AE dash is equal to DE. So I select a point E dash such that AE dash is equal to DE, and then I select another point F dash on this thing, AC, such that AF dash is equal to DF. And then what do? I join these. So when you join this, what will happen? If you see clearly triangle AE dash F dash is congruent to triangle DEF by SAS congruency criteria, isn't it? Because angle AE dash, this side is equal to this side. And let me use another color so that becomes easier for you to understand. Okay, and this side is equal to this side, and boss, this angle is equal to this angle. So hence SAS criteria, these two triangles are congruent. So if these two triangles are congruent, that means corresponding angles must be same. That means angle E is equal to angle E dash, and angle F dash is equal to angle F, isn't it? But my friend, B is equal to E and E is equal to E dash. That means B is equal to E. So if B is equal to E dash, that means line E dash F dash is parallel to BC. Right? And if E dash F dash is parallel to BC, then by using BPT, that is basic proportionality theorem, you can always say AE dash. So hence the conclusion would be AE dash by E dash B is equal to AF dash by F dash C. And hence you can, and AE dash is nothing but DE. So hence, and the corollary to it will be nothing but AE dash by AB is equal to AF dash by AC. And now you can replace AE dash by what? DE, and AF dash by DF. So hence, we now say that even the two sides are proportional. Two sides are proportional. Now you can repeat the same process for angle B and then angle C, and you will see that all the corresponding sides are also proportional. This is just one case. There will be three such cases. In all the three cases, you can prove that the corresponding sides are proportional. So this is the proof for, let's say, AAA similarity criteria. So that means if in two triangles, corresponding angles are equal, then the triangles are similar. Fair enough. So let's move on to our next slide. Okay, so the next thing is a similarity criterion. I don't need to go much into deeper details. Why? Because are because of angle sum property of a triangle. They say that you don't actually need all the three angles to be checked. If two angles are checked to be equal, corresponding angles to be equal, then you're done. Then the two triangles are similar, A, B, C, and this is D, E, F, let's say, D, E, F, and angle A is equal to angle D, and angle B is equal to angle E. Then automatically by angle sum property, what? By angle sum property, which says that sum of the three angles of a triangle is 180 degree. So by angle sum property, angle C is equal to angle F, and then by the previous slide, now we have A similarity, and hence the two triangles will be similar again. So hence, no worries. This is clear to everyone, I believe. Let's move on to the next slide. Okay, triple S similarity criterion. Now they say that if again, so let me use this triangle only. Okay, so let's say it says that triple S is what? If the three sides are proportional. That means AB by DE is equal to BC by EF is equal to CA upon FD. Right? Then triangle ABC is similar to triangle DEF. Mind you guys, while writing similarity, please be very careful in writing the corresponding vertices against each other. So triangle ABC need not be similar to triangle FED, or just let me write it properly. So need not be similar to FED. So because corresponding angle A and F are not same, A and D were same, so hence A and D must be written in the same order. Okay, so all the vertices must be in the same order of equality. That has to be taken care of. Okay, so let's move on to next slide. Next slide. Yeah. Now, if one angle of a triangle is equal to one angle of another triangle and the sides including these sides are in the same ratio, then the triangles are similar. This is nothing but SAS. This is nothing but, wait a minute, this is nothing but SAS. So SAS, right? So now, wait. Right. So yeah. So wait. Okay. Just a minute. So now, next is if two sides. Oh, sorry. So let me first go back to the right number slide. Yeah. If one angle of a triangle is, this should be a triangle, sorry. So if one angle of a triangle is equal to one angle of another triangle, and the side, it's given that E upon DE is equal to AC upon DF, right? If this is happening, if this happens, then we say that triangle ABC is similar to triangle DEF. Triangle DEF. Right? This is nothing but SAS, similarity. Okay, so this is our another similarity criteria. Next. Yeah. Now, so just to summarize before we proceed further, so how many similarity criteria did we learn? One is AAA. This is one. Then second is AA. So these are mostly same. You know. Third is SSS, and fourth is SAS. These are the four similarity criteria. All right. So please be mindful that whenever you are proving similar triangles, one of these criteria has to be used. Okay, fair enough. Let's move ahead and now see applications of similar triangles. If you see, application of similarity, application of similar triangles, and we'll see how these applications turn out to, or let's say, produce these results. So what is that? First of all, I'll try and prove one, and then rest, doesn't take much of a effort to prove the next ones. So if two triangles are equiangular, that means they have same angles, right? If two triangles are equiangular, then the ratio of the corresponding side is same as the ratio of corresponding medians. So, right, so this is, and others are, so hence let me just first draw the triangles. Yeah, so if okay, before we proceed further, I would just like to have a interaction with you. So if you have any doubt so far, you can put forth here, guys. Any problem so far? I'll just wait for your response as well. Any problem so far, guys? Please, you can put it on. You can just type in the comment section so that I get to see, or you can just simply say yes or no, whichever way. Yeah, so that I can see who all are there. I hope you guys are not uh, feeling bored. Yes. Yeah. So later, could you go back to card 12? Okay. Angle bisector theorem boards without proving it another problem. Okay. Uh, I'll go to card number 12 once again, no worries. So let me see what was card number 12. But then, I'm also running short of time. But anyways, okay, let me just complete the entire thing and I'll go back. And then, are we allowed to use angle bisector theorem in boards without proving it in another problem? I would recommend not to do that if you're, because I think you should not be using it because if at all, or if at all you have to require, use it, then you should mention the theorem properly, because you have in lines, don't just use it directly, use, you please mention the let's say the full the description of what angle bisector theorem is at least. Okay, so I can see no other. Okay, very good. So let's move ahead. So now we are on card number 19, and then it says, if two triangles are equiangular, then the ratio of the corresponding sides is same as the ratio of corresponding medians. Okay, equiangular, that means we have to take, equiangular is nothing but equilateral triangle. So let's say, okay, so hence let us take two equilateral triangle. Okay, so anyways, let's not attempt to make it equilateral. So somehow this one and yes, something like that. Okay, now the question is, let's say if you have this as A, B, and C, and this is D, E, F, then what are they saying? If two triangles are equiangular, then the ratio of the corresponding side is the same as the ratio of corresponding median. So very okay. Okay, so to ratio of the corresponding sides is same as the ratio of corresponding medians. So let me just draw a proper median here. So this is the median. So median, what is the median? Median divides the opposite side into two equal parts. Okay, so let's say this is G and H. Okay, now it says that if two, so hence AB, it is given that AB by DE, obviously if the two triangles are similar or equilateral or equiangular, then AB by DE is equal to BC by EF is equal to FD by AC, isn't it? Now, so just a minute, guys. Yeah, so hence now if this is so, then this is equal to AG by DH. Sorry, yeah, D, this is GH. Okay. Okay, and hence the other medians as well. So let's say if this is I, G, H, I, and let's say this is J, then also equal to BI by EJ. Okay. AC by FD. Okay. So did I? Oh, sorry. I wrote it the other way around. Thanks, Prajna, for correcting. So it is AB by DE. AB by DE is equal to BC by EF is equal to CA. I'm sorry. This is wrong. This is wrong, and this has to be corrected. Thanks for correcting. And this is CA upon FD. Okay. Now again, how do you prove? So if these are equiangular, then I don't, this two angle is same. This two angle is same, and it's 60 degrees. And BG is nothing but half of BC, and EH is equal to half of HF, because AG and DH are median. So hence, if you see by angle side, again ABG, triangle ABG, let me write it down. Triangle ABG is similar to triangle DEH. Why? Because AB by ED is equal to half of BC by half of EF. That is nothing but BG and BG upon EH. And then angle ABG is equal to angle DEH, isn't it? So hence, by what similarity criteria? By SAS, these two triangles are similar. Hence, the corresponding sides will be equal to AG upon DH. Okay. Similarly, corresponding sides is same as the ratio corresponding angle bisector segments. What is angles bisector? So in case of equiangular triangles, angle bisectors, altitudes, orthocenter, in center, are all sorry, not centers, altitudes, medians, your internal angle bisector and perpendicular bisectors all are same. Okay, so hence this will be true for all of them. This will be true for all of them. You can try. So what did we learn? One is median. What is median for your this thing? Median is nothing but line segment joining vertex to opposite side of the triangle. This is opposite side opposite midpoint of, or right, midpoint of opposite side of the triangle. This is median. Then altitude. What is altitude? Altitude is nothing but perpendicular from one vertex to the other side, opposite side. This is my altitude. Then there is something called angle bisector segment, angle bisector. So it's very clear. So angle bisectors are nothing but line segment bisecting the angles of the triangle, and then there is perpendicular bisectors. These are four geometrical, elements which we study. So median, altitude, angle bisectors, and perpendicular bisector. So angle bisector is nothing but this is angle bisector. Let's say this is the triangle. So this will be my angle bisector. So this angle is this angle, and this will be my perpendicular bisector, right? So this side is equal to this side, like that. Okay, so you know this. Let's move on next. So if one angle of a triangle is equal, if one angle of a triangle is equal to one angle of another triangle, and the bisector of these angles divide the opposite sides in the same ratio, then the triangles are similar. What does it mean? Let's see. So if one angle of a triangle, so let's say two triangles are there. One, right? A, B, C. It says what? A, B, C, D, E, F. Two triangles are there. What is given? It's given that angle A is equal to angle D. Okay. One angle of a triangle is equal to one angle of another triangle, and the bisector of these equal angles. So let's say, so you have these bisectors of these angles. So what does it mean? This angle is equal to this angle. This angle is equal to this angle. Bisectors of these equal angles divide the opposite side in the same ratio. So it's nothing but the converse of our internal bisector theorem. So if one angle of a triangle is equal to one angle of another triangle, okay, A is equal to D, and the bisectors of these equal angles, that means this A, B, C, and then this is D, E, F, G, let's say, and this is H. Okay, so it is saying that AG is bisecting, AG is angle bisector, and it is dividing the opposite side in the same ratio. That means it's given that BG by GC is equal to EH by HF. Then the two triangles are similar. Sir, if I'm not wrong, it may not always work for perpendicular bisectors as they don't pass through the opposite verse. Oh, in card number 19 you're talking about? Just let me see. What was that? Okay, there's a doubt. So it says if two triangles are equiangular, then the ratio of the corresponding side is same as the ratio of the corresponding altitudes. Yeah, that's true, because they are, so in case of equiangular triangle, I was just mentioning about all the four elements because those four elements are usually, so I was just trying to recap the four elements of the triangle which are usually utilized in problem solving. So yes, it will not hold true for the perpendicular bisectors, as it is rightly pointed out that perpendicular bisectors will not pass through the vertices. Very true. Correct. Thanks for correcting. So card 22 is this, and we were explaining this to you. Yeah. So hence it's given that angle A is equal to angle D, and BG by GC is equal to EH by HF. It is given. Then you have to prove that A or basically triangle ABC. So hence, if that is true, if these two criteria are fulfilled, then triangle ABC is similar to triangle DEF. Right now, so hence, what did we learn from internal bisector theorem? If you remember, BG by GC is equal to AB by AC. Internal bisector theorem says that in a triangle, if there's an internal bisector of an angle, let's say AG is the internal bisector, then AB by AC will be equal to BG by GC. That's what we learned in internal bisector theorem. So hence, AB by AC. So here, AB by AC is equal to BG by GC. Will be equal to, similarly here, will be equal to DE by DF. Sorry, DF. Sorry. So this is DE by DF. By DF. Now AB by AC is equal to DE by DF, and angle A is equal to angle D. Right? It's already given. One angle is given from here. Angle A is equal to angle D. So by SAS criteria, side criteria, those two triangles are similar. Okay. So this is also done, I think. Next. So if two sides and a median bisecting one of these sides of a triangle are respectively proportional to the two sides and the corresponding median of another triangle, then the triangles are similar. Let me explain. Looks a little complex while reading it. So what does it say? So hence you should do like this. Two sides, okay? So two sides of and a median bisecting one of these sides of a triangle. So let's first make one triangle. One triangle is like that. So let's say A, B, and C. Let's say two sides. So let's say let's pick up AB and AC, these two sides, and one of these, and a median bisecting one of these sides. So let me pick up this AC, and let's say this point is D. Okay, so triangle are respectively proportional to the two sides. So we'll have to have another triangle. Let's say another triangle like that. It's proportional to, let's say, P, Q, R, and S, right? So it is saying AB by AC is equal to, if two sides and a median, I'm not sure, I'm sorry, this is not AB by AC, it's basically AB by PQ, AB by PQ is equal to AC by PR and is equal to BD by QS. If this is so, then triangle ABC is similar to triangle PQR. This is my problem. So hence again, how to read two sides and a median bisecting one of these sides. So I pick two sides, AB and BC, and median bisecting one of these two sides. So one of these two sides is, let's say, AC. Pick D as the midpoint. So BD becomes the median. So two sides and the corresponding median is BD. So AB, and then they are proportional to the similar setup in another triangle. So hence AB upon PQ is equal to AC upon PR is equal to BD upon QS. Then the two triangles are similar. This we have to prove. Okay, fair enough. So how to prove? These two things now. So clearly AB by PQ is given. We have to prove that these two triangles are, when will these two triangles be similar? You have to prove AB by PQ is equal to somehow AD by it is already given that AC. It's already given that AB by PQ is equal to AC by PR. It's given, and by AC by PR is given. So hence it will also be equal to AD upon PS. AD upon PS. Why? Because AD is nothing but half of AC, and PS is nothing but half of PR, half of PR. Okay, so when that is true, that means if you consider these two triangles, which two? Yeah, so in triangle, so let me just write here in triangle ABD and triangle PQS. Okay, what's given? AB by PQ is already given equal to, or we just proved it that it is equal to AD by PS, and by given also criteria also it is equal to BD upon QS. It's here. So AB by PQ is equal to BD by QS, and we just proved that is equal to AD by PS also here. So that means by SSS, these two triangles are similar. Which two? These two triangles are similar. When these two triangles are similar, my friend, then this angle must be equal. So hence, if these two triangles are equal, then what will happen? AB by so these two triangles are equal, and the corresponding sides are anyways given to be equal. Why? So if you see AB by PQ is equal to BD by PR. I'm sorry, BD by no, you can't take this one. AC by PR. If you see, AB by PQ is equal to AC by PR. AB by PQ is equal to AC by PR, and these two angles we just proved equal. So hence, the two triangles must be similar. Okay. So this is slide number 21. Next. Let's go to next slide. If two sides and a median bisecting the third side of a triangle are respectively proportional. Now, in the previous case, what did we learn? In the previous case, it was this was slide number 21, isn't it? So in the previous case, there were two sides and a median bisecting one of these sides. But in the next slide, this is a median bisecting the third side. So if you see the next slide, the question is, if two sides and a median. So again, if two sides, these are two triangles, triangle ABC and let's say PQR, triangle ABC and triangle PQR. What does it say? It says that if two sides and a median bisecting the third side of a triangle. So this is, let me pick AB and PQ. So let's say these two sides are corresponding sides. These two sides are corresponding sides. So AB and PQ and AC and PR, and the third median of the third side. Yeah, bisecting the third side. So this is a median. Let's say A, B, C. Let's say this is D and this is S. Okay, they are proportional. Then again, the two triangles are similar. What does it mean? It says that if AB upon PQ is equal to AC, if AB upon PQ is equal to AC upon what? PR is equal to AD upon PS, then these two triangles, triangle ABC is similar to triangle PQR. Right? So then triangle ABC is similar to triangle PQR. How to prove this? So okay, this is also proportional. So I'm just making a symbol to identify that these three sides are proportional. Now again, how would you prove it? So if you see, if you can somehow prove two sides and a median bisecting the third side of a triangle are respectively proportional to the two sides and the corresponding median of another triangle, then the triangles are similar. So that means, so what has to be proven? If you somehow prove that either the corresponding angles are same, or the third side, that is BC by QR, is also same, or it is equal, somehow you can say that BC is BC by QR. Somehow if you prove this, then you're done. So let's see how what can be done now. Medians are proportional. Okay, fair enough. That means, okay, so what to do in this case? So basically, just give me a moment. Yeah, so he is saying something. You can use triple S right in card 21. Card 21, just a moment. What was triple S in card 21? to the third side, corresponding medium of other. I didn't get this, Ruhi, so I'll come back to that. Never mind. So you will come to this doubt. Let me just cover this doubt, this thing first. So this question gives you AB by PQ is equal to AC by PR, and it is equal to AD by PS. Then you have to prove that the this thing is, if two sides and a median bisecting the third side of triangle respectively proportional to two sides, okay, then the triangles are similar. So how to do it? So if this is the third side, then okay, this is the median. So this is being bisected here. So BD is equal to DC, and QS is equal to SR. Okay, so what to do? So how do we go about it? What was the proof? AB by PQ is given equal. Fair enough. And AC by PR is also equal. AC by PR. Let's close those. AC by PR, and this is AD by PS. These three things are given. Okay. So how do we prove this? Okay. So yeah. Okay, so basically, yeah, either you have to do by, you can do a construction here. So it doesn't seem to be, so let's say, yeah, if I extend the median to make it equal and then joins, what do I get? I get, okay, yeah. Yeah. Hence, if you that you have to, that's fine. Now this side. Okay, and this side is this, and this angle is this equal to this angle. That means these two, angle ABD and let's say CDE, CDE are congruent. That means AB and C is what? Okay. So what? Okay, and then yes, so what will happen? So let's see if I extend it, then similar. How does it help me? So AB by PQ, AB by PQ is equal to AD by PS. That's fine. Okay. 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 So primarily, if I extend this, when okay, these two are also congruent, then you can some BD by somehow I have to prove that this by this. Okay, now wait a minute. I will extend this. Okay, I will extend that. Just give me a moment. Okay, so these two triangles are also congruent. That's fine. And then AD by or we need to prove it by, wait a minute, guys. Okay. I'm okay, kind of, let's say we are stuck, but never mind, we'll somehow. So AB, if I extend AD DE, if I extend AD to DE, okay, Okay, so these two sides are just close the door, guys. So oh, are you guys there? Hello. It's showing loss of hello. Hello, can you guys hear me? Hello. You guys here? Hello. Hello. Guys, you there? You just respond by saying yes in the segment. I understand that you're there. Hello, you there? Hello. Guys, you're there? I'm afraid I don't know whether you're there. Hello, you there? Hello? Hello? Guys, are you able to hear me? I see a lot of contact. Hello? 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 Guys, I'm afraid. Hello, the screen is so now okay. Just a minute, it will stable. Just a minute, it gets stable. Maybe because of some internet issue. Just hold on. Just give me 2-3 minutes. 2 minutes at least. I'll just refresh it. Yeah, is it fine now? Hello? I can't see your responses. Just a minute. Oh, okay. So my screen was frozen. So thanks. Yes. Now, thanks, guys. Okay. There is lot of yes, sir. Good. Sorry, my screen was totally frozen. So there was some maybe fraction. Yes. So anyone could attempt this. Oh, wait. I have to just make it full screen. Give me a moment, please. Full screen. Okay. So this has to be made full screen. Yeah. So in case you are, whenever you are if there is some kind of a frozen screen, you just let me know through WhatsApp. That's fine. Okay. So I was trying to go through it. Okay. Now, let me do one thing quickly, guys. Let's park it for time. It's not, frankly speaking, it's not getting stuck here. So let's I'm not, I'll just, let me just cover the slides first, and then slide number 12 and 22 are left. So let me just first, in the interest of time, let's first cover and then come back. So we'll park 22 and 12. Okay. Next is the ratio of the areas of two similar triangles is equal to the ratio of the squares of any two corresponding sides. Square of corresponding altitudes, medians, and angle bisector segments. So let me first quickly. Okay. Okay. Fair enough. So anyways, we'll come back to this side. No worries. So let's say the ratio of ratio of areas of two similar triangles is equal to the ratio of the squares of any two corresponding sides. So you have already done this multiple number of times. So again, quick recap: this one, and then this one again, and then yeah. So yeah, the thing is, areas of ratio of areas of two similar triangles is equal to the ratio of any two corresponding sides. So let's say A, B, C, and D, E, F. Okay, ratio of the areas of two similar triangles is equal to the ratio of the squares of any two corresponding sides. Okay, so it's very, so what is that? Area of triangle ABC by area of triangle DEF. DEF is equal to nothing but AB square by DE square is equal to BC square by EF square is equal to CA square by FD square. Right? Again, how to prove that? Again, you have to drop a perpendicular from here. Right? DE, let's say BC, it is P and this is Q. Okay, and then this is a perpendicular you dropped. Okay, and then you know that it's very easy. Triangle ABC, quickly I'll recap it. Triangle ABC divided by triangle DEF into BC into AP upon half into base into height, that is EF into DQ. Right, now half get cancelled. Now somehow if I prove that AP by DQ is equal to, let's say, or if we prove that somehow AB upon DE is equal to AP upon DQ, then we are done, and it is easily, easily noticeable. How? Because if you see, this angle is equal to this angle, and AP and this is 90 degrees. So I'm writing here for the lack of space here. So I'm writing here. So let's say triangle, consider triangle ABP and triangle ABP and DEQ. Okay. So what AB? Okay, AB. Yeah. So in these two triangles, angle B is equal to angle E. Sorry. And what? Angle APB is equal to angle DQE is equal to 90 degrees. APB is equal to DQ is equal to 90 degrees. That means these two triangles, which two? These two triangles are similar. These two triangles are similar. If these two triangles are similar, then what can I say? I can say AB by DE is equal to AP by DQ. And if you use this in this, so this is what we had to prove, and hence this can be written as BC. Okay, so it was AB by D is equal to AP by DQ, and since these two triangles were similar, so this could be also equal to BC upon EF, because they were similar triangles. So hence AB by DE is equal to AP by DQ, which is equal to BC by EF. Why BC by EF? Because AB by DE was equal to BC by EF, because these two triangles were similar. So hence from here you can say this is BC square by EF square. Okay, now clearly square You can see instead of BC by EF, you can write AP by DQ here. Why? Because BC by E is equal to AP by DQ. So this is also equal to AP square by DQ square. This is also done. Squares of corresponding medians. So we just in previous slides you saw that in if two triangles are similar, then their corresponding median is also proportional, right? In the previous slides. So this is also done. We also saw this in the previous slide. So angle bisectors were also there. So if for two similar triangles, angle bisectors are also similar. Sorry, also proportional. Okay, clear. So this is card number 23. So this is another. If you remember, we were talking about. Sorry. Yeah. So here is similarity of triangle applications is lots of we saw the lots of applications and including the ratio of the areas. Okay. Now let's go to card number 24. Yeah. If the areas of two similar triangles are equal, then the triangles are congruent. That is, equal and similar triangles are congruent. Okay, so this also follows out from the so they are saying if the areas of two similar triangles. So two similar triangles there are two similar triangles ABC and PQR, and their area is same. So area is same. That means area of triangle ABC is equal to area of triangle PQR. That means area of triangle ABC divided by PQR1, which is equal to nothing but AB square by PQ square is equal to BC square by QR square is equal to CA square by PR square. And all the ratios are 1. That means from all this you can say AB is equal to PQ and BC is equal to QR and CA is equal to PR. Hence, this side is equal to this side is equal to this side, and this side is equal to this side. So these two triangles are congruent. Okay, by SSS criteria. Okay, next slide is if a perpendicular is drawn from the vertex of the right angle of an angle to the hypotenuse, then the triangles on both sides of the perpendicular are similar to the whole triangle. And so another, this we have asked you in multiple occasions also. So there's a right angle triangle. First, we have dropped a perpendicular from here. So that says if a perpendicular is drawn from the vertex of the right angle of a right triangle. So this is the right triangle. Right angle dropped a perpendicular. Let's say this is A, this is B, this is C, and this is D. ABD is dropped, BD is perpendicular dropped down AC. Perfect. Then the triangles on both sides of the perpendicular, that means that they are saying that triangle ADB is similar to triangle ABC. And it's together is similar to, so ADB is similar to ABC, and triangle ABC is similar to angle ABC is similar to CDB, angle BDC, isn't it? So hence if you see angle ADB is similar to ABC. Very easy. Why? Because in these two triangles, if you see, angle A is common. Angle A is same. So what all angles we are taking? We are taking this one, and let me choose another color to highlight it in different colors. So let's say I'm choosing this one. These two triangles. Okay, so I'm drawing just the outline of it. So if you see, this is common angle to both. This 90 degree is equal to this 90 degree. Hence, by AA similarity, they are similar. So angle A is equal to angle A. Angle D, which is 90 degrees, is equal to angle B, which is again 90 degrees. So hence, both are similar. Now, between ABC and CDB, same thing happens. So we are saying triangle ABC and triangle CDB, these two. All right. So hence common angle is C, both, and D is perpendicular, angle D. This angle is 90 degree, and this angle is 90 degrees. So hence B is equal to D, right? Perpendicular, both are perpendicular. So hence again this is similar. So hence they are similar to each other. If you remember, I had given you this question sometime back in your module test. Okay, fair enough. So let's move ahead. We are running short of time. We have 4 slides more to go, so we'll complete. Okay, Pythagoras theorem. In a right triangle, the square of hypotenuse. This is so many times you would have done. So let me not go again. So if you want, again, this is what the proof looks like. ABC, Pythagoras theorem says AC square is equal to AB square plus BC square. You have to use what? First of all, you have to use triangle ADB is similar to triangle ABC. And then using this, you have to find out one relationship between AD's, let's say between the 2 sides, that is the corresponding sides, and then using the other 2 sides, that is triangle CDB is similar to triangle CBA. Using these 2 triangles, these 2 similarity, you can prove that. I am not going in the details again. Yeah. So if triangle 1 is similar to triangle 2 and triangle 3 is also similar to triangle 2, can we just say that triangle A and triangle 3 are similar, or do we have to prove it separately? No, you don't need to. You don't need to prove it separately, because it's clear, evident from. Acha, let me do it once again. So let's say I'm taking this. So triangle, clearly this is done. When ADB is similar to ABC and CBD is, but you have to just maintain the order of the vertices. So let's say ADB is similar to triangle ABC is similar to triangle what? C remains at C's position, B goes to D and becomes BDC. Yeah. So, and this is how it is. Okay. So you can do that directly. You don't need to prove them again. Okay, next. So this is also done. So Pythagoras theorem, I'm again leaving it on to you to do the next slide. Converse of Pythagoras. So converse of Pythagoras theorem is again by contradiction. You can again use. So what is converse of Pythagoras theorem? It says that in a triangle ABC, if AC square is equal to AB square plus BC square, then AB angle ABC is right angle 90 degrees. You have to prove that. Okay. Yeah. So this is okay. So this is also, how do you prove that? So let us say, there are 2 possibilities, either angle ABC. Let's say we start with contradiction again, so you can do that. Again, I'll just give it, I'm not going to the details again. So let's say if, let's say ABC is not equal to 90 degrees, then either ABC is greater than 90 degrees or angle ABC is less than 90 degrees. Let's say ABC is greater than 90 degrees. That means you can find a point C dash such that ABC dash is 90 degrees. Then you can write by Pythagoras theorem what? That AC dash square to E square plus BC dash square. This is by Pythagoras theorem. And then by giving, you can write AC square is equal to AB square plus what? BC square. Okay, and then you subtract both. You will get AC dash square minus AC square is equal to BC dash square minus BC square. Okay, and then from here I'll use this. So from here you can write AC plus into AC dash minus AC, or AC dash plus AC is equal to BC dash plus BC into BC dash minus BC. Okay. Okay. Now, what do I learn? This is a positive quantity, so AC dash minus AC is negative. Okay, so this quantity is AC dash minus AC is clearly less than 0. Why? Because AC dash is smaller than AC, so this quantity is negative. Now this is also positive. That means BC dash minus BC must also be less than 0, because BC, this is positive, this is positive, this is positive, and if this is negative, then this is also negative. That means BC dash is less than BC. BC dash is less than BC dash is less than BC. Okay, so I'm running short of time and space both. So hence, if BC dash is less than BC, that means what? Opposite. So angle BC dash. So angle BCC dash is less than BCC dash. Angle BCC dash. Opposite angles should also be in the same ratio. So in this triangle BC dash C, you will BCC dash BCC dash C. So basically this side is less than this side. So this angle will be less than this angle. Okay, this angle is less than this angle. So I'm writing here, don't mind. So that means angle BC dash C is less than angle BCC dash. Okay. Okay, BC dash C. So BC dash C is less than BCC dash. That means what is this? 180 degree minus angle AC dash B is less than yeah. So hence 180. There can be multiple this thing. I'm just giving you one logical proof which can also be used. So 180 degrees minus AC dash B. This is my BC dash C is less than angle BCC dash. Okay. So okay, yeah. No. So we actually wait a minute. So we actually BCC dash is what did we prove? BC dash is less than BC. So BCC dash is less than, oh, other way around. Sorry, this, yes, this is other way around. Yeah, so this will be like that. So BC dash C is greater than, I need some, space here. Wait a minute. So eventually you will have to prove, what will have to be proven? That this, clearly this angle is BC, this angle is more than that, and yeah. So basically what will happen? BC dash C is greater than angle BCC dash. So there is, yeah. So one Mehul is suggesting you can even prove by constructing another right triangle such that any two sides of the triangle is equal to any two sides. You can do that. Yeah, you can construct another triangle, but it will be similar to this approach, I think. So let us first try and resolve this, because nothing should go unresolved. So hence I'm saying, if I think we are doing correctly, BC dash, yeah, so AC dash minus AC is less than 0, and so hence BC dash must be less than BC. BC dash is less than BC. Okay, now yes, BC dash. So we have to prove that somehow BC dash is BC dash is greater than BC. Somehow that, if that is proven, then we are done. Okay, so let me just have some space to solve. Let me do it like that. Okay, let me just, yeah, don't worry guys, I'll take just 10 minutes of yours and we're done. So basically we are doing this. This is a triangle. There was some small space, so let me just do it. Just bear with me for some time and we are done. So ABC, and let's say they are saying that AC square is equal to BC square plus AB square. Okay, and then they are saying that prove that angle ABC is equal to 90 degrees. Okay, now we are saying, let's say it's not 90 degrees, and angle, now we are saying, let us say angle ABC dash is equal to 90 degrees. Let us say, let's say. Okay, then by this, what do I get? I get by Pythagoras theorem, AC dash square is equal to AB square plus BC dash square. And here it is, here it is, given is AC square is equal to AB square plus BC square. So let me subtract both of them. So I'll get AC square minus AC dash square is equal to BC square minus BC. So that I can write as AC minus AC dash, AC minus AC dash into AC dash is equal to BC minus into BC plus BC dash. Okay. Now clearly this is greater than 0. This is also greater than 0. AC minus AC dash, that is CC dash, this is also greater than 0. That means BC minus BC dash is greater than 0. Okay. BC minus BC AC minus AC dash is greater than 0, and this is positive, so BC square. Yeah, so BC minus BC dash is greater than 0. So means I have to just contradict this. If BC is greater than, if BC is less than BC dash, my assumption was wrong. This assumption was wrong. So let's try and prove that. Now clearly BC minus BC dash is greater than 0. That means what? Angle or BC is greater than BC dash. This is what that means. That means what does it mean? It means angle, opposite angle. So opposite angle is BC dash C is greater than angle BC dash, opposite is BCC dash, right? So BC dash C is greater than angle BCC dash. Okay, now BC dash C can be written as 180 degrees minus what? A C dash B, and this is greater than angle BCC dash. Okay. Now, so that means what? 180 degrees is greater than angle AC dash B plus angle BCC dash. Now check what is AC dash. If you see angle AC dash B, angle AC dash B is this angle. I can't show it here. So degree angle is greater than AC dash B plus BCC dash. So this plus this, isn't it? So this is what they are. See how because yeah, so 180 degree angle is greater than 180 degree angle is greater than, sorry guys, it's getting a little delayed. So this is equal to angle AC dash B can be written as angle 2 I think we are heading in the wrong direction. So just let me see what all are left, and then yeah, sorry for interruption once again. So we'll just cover converse of Pythagoras theorem is there. So what all slides are left? I think three more theorems. Yeah. So these three theorems probably will take up in the next class, but we'll cover at least the theorem part of it. Okay, so that angle got little deviated. Let me just see. I'll just try and prove using our conventional method. So converse of this thing is very simple. It didn't work. So let me just try this. So what Mehul was suggesting is you have to draw another. That's a conventional method. So since it's a board exam, let's not try. So let's say A B A B A B A B C is the ABC is the triangle where AC square is equal to AB square plus BC square. Okay, and then we have to do what to prove that angle B is equal to 90 degrees. So what you do is you draw another triangle. So this is your NCRT proof maybe. So this is DEF. This is DEF you draw such that what is that? D is equal to AB. So AB is equal to DE and EF is equal to BC or BC is equal to EF and angle E is equal to 90 degrees. So you make it like that. You make a triangle equal to 90 degrees. Now, clearly, if in this triangle, this is construction. So if you do that, you will get what? DF square is equal to DE square plus EF square. Pythagoras theorem, right? And DF square hence can be written as AB square plus BC square and BC construction F. So hence, but using this you can write. But AB square plus BC square was AC square. So DF square AB square plus BC square it's given from here is AC square. So write AC square. So hence DF is equal to AC. So hence in both these triangles, if you see AB is equal to DE and BC is equal to EF and AC is equal to DF, hence angle is triangle DEF, hence C is equal to which is DEF. This is a conventional proof. So if at all there is this proof, you can use this method. So hence construct another triangle with corresponding these equals, and then AC square is equal to, you can do that. Prove the two triangles to be congruent and then prove that this is equal to 90 degrees. This is how the conventional proof goes. I will again, we in the class we attempted another proving method. We'll again solve and send it back to you. I'll just read out these theorems so that this thing is complete. So hence in any triangle the sum equal to twice the square of half. This is we have done in the class as well. So it says if this is a triangle ABC, this is actually called Apollonius theorem. So in any triangle, sum of the squares of any two sides, so AB square plus AC square is equal to the twice the square of half the third side and the median, which so hence it is equal to twice the square of half the third side. So this is D. So 2 times DC square plus AD square. This is Apollonius theorem. We have discussed the proof in our classes, right? This is Apollonius theorem. Again, you have to use Pythagoras theorem to. So what you need to do is you need to drop a perpendicular here. Drop a perpendicular A, B, C. Let's say put it P, and then use Pythagoras theorem And express AB square in terms of AP and BP, express AC square in terms of AP and PC, and then express. So there are three Pythagoras theorems you'll write AC square equations. You'll write AC square is equal to AP square plus PC square, and then you'll also write AD square is equal to AP square plus PD square, and then you'll write AB square is equal to AP square plus BP square. And using these three, you eliminate AP, and another equation is BD is equal to DC is equal to half of BC. Using all this, you eliminate AP and every point related to P, and you will get this. Okay. So this was Apollonius theorem proof. Now next, we are almost done. So let's go to card number 29. 3 times the sum of the square of the sides of a triangle is equal to 4 times the sum of the squares of the medians of the triangle. Yes, this is again a very important theorem. You need to know this, but then you avoid using them directly in your problem solving. Actually, there will not be any direct application, but yeah. So what is this theorem? This theorem says that, okay, this is ABC, and it says 3 times the sum of the squares, 3 times AB square plus BC square CA square is equal to, let's say these are the medians, and this is the direct application of the previous theorem, that is the Apollonius theorem, right? So let's say this is DEF is equal to 4 times BD square plus AF square plus EC square. Okay, AF square 3 times AB square plus BC square plus CS square is equal to 4 times BD square plus AF square plus EC square. How to prove? Again, use this Apollonius theorem. Apollonius theorem says what? AB square plus AC square is equal to twice of AF square plus twice of AF square plus BF square. And similarly, you times and then eliminate. So AB square, and then you write BC square plus CA square is equal to 2 times BCCA is 2 times CE square plus BE square. And then again you write third one, this is 1, this is 2, and then third word I am writing here, and that is nothing but CA square plus AB square, CA square plus, sorry, not AB plus AC we wrote, and BC and CA I wrote. Then I have to write AB square plus BC square. Sorry, this is BC square. So BC square plus AB square, BC square plus AB square is nothing but twice of BD square plus BC square. Using these three, add all of them together, you will get this relation by saying that. And you know that how do you replace DC? So DC is nothing but, CD is nothing but half of AC. You have to write that. And BF is nothing but, or BF is equal to, wherever BF is, there is BF. So BF can be written as half of BC, and BE is equal to half of AB. So using these three and these three also together, you will get this relationship. You'll have to just eliminate. Fair enough. So this is card number 29. So this is also done. And what next? Left with this one. 3 times the square of any side of an equilateral triangle is equal to 4 times the square of the altitude. This is again fallout of the previous one. So hence, if you see, this is nothing but, if there is an equilateral triangle, so if there is an equilateral triangle, this is equilateral triangle, and they are saying that 3 times the square of any side of an equilateral triangle. So let's say A, B, C. Right? So 3 times AB square is equal to 4 times the square of the altitude. 4 times the sine, or A, B, C, D. And you can see this direct repercussion or direct fallout of the previous one. Why? The previous one was this 3 times what? AB square 3 times the square of any side of an equilateral. Yeah. So AB square plus BC square plus AB square plus BC square plus what CA square is equal to 4 times the median. And in this equilateral triangle case, median is equal to altitude. So 4 AD square plus, let's say AD BE, this is BE square plus CF square, right? Now, in case of equilateral triangle, AB is equal to BC is equal to CA, right? All sides are equal, and altitudes and medians are also equal. So you can write AD is equal to BE is equal to CF. Using these three, what can you say from here? So let's write this color. Let me change the color a bit. Yes. So if from here, what will happen? It is nothing but 3 square is equal to 4 times AD square will be equal to B square equals to CF square from here. So hence 3 gets cancelled. So hence 3 AB square equals 4 AD square. Right. So this is your summary of the entire this. Now what remains is problem solving. Obviously, these are the points to keep in your mind while you are trying to solve problems. So beyond these, no theorem and no application will be there. All the questions you will be getting, you will be having these only theorems useful. Now always keep in mind, I told you, what did I tell you? That just a minute, I will show you. Yes, so this is the basic information. Yeah, basic information says that the moment you see questions related to triangle, what should come to your mind? First, use of similarity or in all probability, one or max couple of things to proofs related this thing, theorem proving related stuff. Otherwise, mostly if there will be proof, there will not be a direct theorem. There will be application of these. So always in your mind, the moment you see a triangle, application of basic proportionality theorem or similarity of triangles or application of Pythagoras theorem. Corresponding squares of sides and all that will be included. So once you have the list of all the theorem in front of you, then you will be able to think through the problem and solve it. So again, there will be, if the problem is related to ratios, or if you see lots of parallel lines in the diagram, or if they are in the form of square. So the moment it is in the form of square, then either the application of Pythagoras theorem, or it will be the ratio of areas. These are the only two techniques through which this can be solved. Okay, guys. So if you have any queries, questions, you can always reach out to me, and that we are recording a lot of problem solving videos which are in progress. If you want any particular problem to be solved and sent back to you, you can always reach out to me or any of the other faculty members, or you can also mention in the comment section also. No problems. Session usual, we I actually got a little bit prolonged. No worries. We'll try to confine to 2-hour session from. But I hope it was useful. So next class, I believe, is on Friday, and has been circulated to all of you. Please try to attend the session so that it becomes a quick revision of all that is there. At least it will give you an overview of the entire which is there, and it will be there in your mind. Okay, so yeah, so let's call it a day, and then we'll meet again. Thanks for your time, and keep watching the problem solving videos and keep solving worksheets. We have shared a lot of content material in the drive as well, so please utilize them. Try to solve as possible. This is the only way you can improve your score now. Okay, thanks a lot. So we will close here. Thanks for your time. Good night.